So let's do another element video. We got lots of great feedback from the first element video, and I've incorporated that. So, for instance, Lorna thought it was a bad idea for me to be doing science experiments involving flaming substances with bare feet. So now I have laboratory grade flip-flops on. Okay, and Mommy thought any experiments involving flaming molten alkali metals should not be done on a plastic tub. And I have a solution for that too. We now have a laboratory grade aluminum work surface. Okay, so because Marie's learning about elements in science, all of our experiments are going to have to use pure elements. That's going to be the rule. Okay, so I think the first experiment we should do involves sulfur and zinc. So I have these two elements right here. And you guys can take a look at them. That's zinc. You can hold it, Zach. And that is sulfur. So you can see that sulfur is kind of a bright yellow element. These are both powdered because we want them powdered for the reaction we're going to do. And zinc is a metal, so it's kind of a grayish substance, right? So why don't you give those back to me? And what we're going to do is we're going to mix these together. So I'm going to mix them together in this beaker and put on some gloves. And while I'm doing this, I have a question for you, Marie. So I'm starting out with 15 grams of sulfur. This is actually kind of a trick question. I'm starting out with 15 grams of sulfur, and I'm going to try to make the sulfur react with the zinc to form a compound called zinc sulfide. So I want each sulfur atom to react with one zinc atom. So if I have 15 grams of sulfur, how many grams of zinc am I going to need to have the same number of sulfur atoms and zinc atoms?
15.
Well, I told you it was a bit of a trick question, right? It turns out if you consult your periodic tables that are under your chairs, you will notice that the atomic weight of zinc is twice the atomic weight of sulfur. What that means is that each zinc atom weighs twice as much as a sulfur atom. So if we have 15 grams of sulfur atoms and we want the same number of zinc atoms, how many grams of zinc do we need?
7.5.
Zinc atoms are twice as heavy, so we need twice the weight of zinc.
30.
That's right, we need 30 grams of zinc. And that's what we have, and so we're going to mix this up. Now, this particular mixture is not very sensitive to friction, but to be safe, I'm going to mix it up with a wooden dowel. Mix it really well. Okay, so now we have zinc and sulfur mixed together, but the thing is this is not a reaction. We have not created zinc sulfide. In fact, we just have a bunch of zinc powder and sulfur powder together. So we need to figure out a way to make this react. So what I'm going to do is I'm going to start out by just putting it on here while we talk about what our options are. So let's put it right here. Now sometimes when you put elements together, they won't just react on their own. However, there's a good way to sometimes get a reaction started, which is to add some heat. And do you know why heat might help a chemical reaction occur? what happens to molecules when you heat them up? What do?
They come together.
They start moving faster, right?
Yeah.
And so you have sulfur atoms and zinc atoms bouncing around, and if you heat them up, they're going to bounce around more quickly, and they're going to hit each other occasionally, and they might combine into a compound. Okay? So the other interesting thing about the reaction that we're going to do, which is to react zinc and sulfur to produce zinc sulfide, is that it's called an exothermic reaction. That means it's a reaction that gives off heat. So imagine this, you have a zinc atom and a sulfur atom. You put a little bit of heat in, they combine together, and they give off some heat. And that heat they give off is absorbed by 2 zinc atoms and 2 sulfur atoms, which then combine together, and they give off twice as much heat. And that makes 4 zinc and 4 sulfur atoms combine, and they give off even more heat. Okay? That's called a chain reaction because it keeps getting bigger and bigger as the reaction starts. It's kind of like a snowball rolling down a hill. So, in order to get the ball rolling, we have to add a little bit of heat. And there's a number of ways we could add heat. We could use a match or maybe a hot rod or something like that. But I think for maximum excitement and suspense, there's no getting around using a fuse.
What?
So we'll stick a fuse in here.
Ouch.
Make sense? So
Looks like gunpowder to me.
So let's so let's light the fuse. And right now, remember I said we have a mixture. And the reason it's a mixture is if you looked very closely at this under a magnifying glass, you would still see gray zinc particles and yellow sulfur particles. They haven't really combined into a new compound. But there's a way we can figure out whether we've created zinc sulfide, which is a new compound, which is that it has completely different properties. It's actually white rather than gray or yellow. So we'll have to watch closely and see if we can detect any change in color from gray to white. Okay? Okay, so here we go.
Alright.
Wow! I think it worked.
Oh, look! It's kind of like flashing lights, see?
Yeah. I see a huge cloud of white smoke in the
Oh
garage.
my goodness.
Now that's not actually smoke. That's actually zinc sulfide powder, which is a white powder. And you can see all this white material here is also more zinc sulfide. And remember I said this is an exothermic reaction. If we look at this, we'll see that the heat of this reaction actually started to melt this metal plate. That shows how much heat was given off. And even though this reaction looked like it was burning, it wasn't actually burning because no oxygen was needed. It was just zinc and sulfur combining to form a compound. So this reaction could happen in the vacuum of outer space. It doesn't need any oxygen. So it's not actually burning, but you can see it still gave off a lot of heat. So that was our first experiment, and I think we should move on to another pair of elements, and that we'll see if we can make react. And the elements I think we're going to use this next experiment are chlorine and iron. Now chlorine is a gas, and it's got this one downside, which is it turns out it's a poisonous gas. So in order to do a chlorine experiment, we're going to have to do a little bit of setup. So I'm going to clean up this big zinc sulfide mess I made before Mommy sees it. And then we'll get set up for a chlorine experiment. Next experiment with elements is going to require us to generate some chlorine. And I mentioned to you that chlorine is a gas. So we're going to be generating it, and because it turns out it's a poisonous gas, we're going to generate it in a way that keeps it inside this container here, this glass beaker. Okay, we're going to do that by displacing water with chlorine gas. So I'm going to get this reaction started and then we'll talk a little bit more about chlorine. So let me first of all put this glass tube in here. And I'm not going to describe exactly what chemicals I'm using for safety reasons, but this acid turns out to be hydrochloric acid, and this is a little tricky. I'm going to pour a little bit of this in. And it's going to react and start forming chlorine gas, but I have to pour it in very slowly. So what you're going to notice is that, see how there's a green gas inside the Erlenmeyer flask? See how it looks greenish? That's chlorine gas being generated, and it's going to go through this tube. And see how this glass tube has a nice bend in it? We were learning how to do basic glass blowing the other night. We were able to bend that tube, and the chlorine is going to go through the rubber tubing into this beaker. Okay, we have some chlorine in here, and now I was mostly getting rid of the air in the Erlenmeyer flask, and so now what we're going to do is fill up this big beaker with chlorine. Now, chlorine is a very distinctive smell, and once you've smelled it, you'll never kind of forget the smell, and in fact, it'll probably smell a little bit familiar to you, because it's the same smell as chlorine in the pool. It also smells a little bit like bleach, laundry bleach. And luckily our noses are very sensitive to chlorine, and so we can detect when it's in the atmosphere and know that it might be reaching a dangerous concentration.
Water with chlorine.
That's right. The chlorine goes up into the beaker and it pushes the water out. So that keeps the chlorine in a sealed container, and only the water leaves the beaker. So what I'm going to do, it's actually starting to float because it is lighter than the water. So let's not let it get away. I'm going to put this under here so we capture any excess chlorine. And at this point, I think we should just pause for a minute, and we're going to let the garage air out a little bit just in case some chlorine got into the atmosphere. And then we'll do an experiment with our beaker of chlorine, okay? Okay. Okay, we're back, and we've moved our apparatus out of the way, so now we just have our beaker of chlorine gas. And Marie, if you want to consult your periodic table, you'll see that chlorine is in group 17, which is right over here, and it has 7 electrons in its outer shell. It has a valence of 7, which means it's missing 1 electron, and it really, really wants to grab that extra electron, which makes it a very reactive gas. It will react with many things that you wouldn't think a gas would react with. And in fact, all the halogens are very reactive because they're all missing 1 electron. That's why they're in that column. So what we're going to do is we're going to try to see if we can make chlorine react with iron. Now, iron is not a very reactive substance. There's iron everywhere in our world, and it really doesn't do much. It just kind of sits there, right? Other than rust a little bit. But I think we can make a little more interesting reaction with chlorine and iron. So what I'm going to do is we're going to take our beaker of chlorine, and we have some steel wool here. And I'm going to get it warm again, which will help the reaction. I'm going to warm up the steel wool, and I'm going to put it in the beaker, and we'll see what happens. Get a little warm, put it in here. Well, see what it's doing? The iron and the chlorine are actually reacting together to form a new compound called ferric chloride. That's that brown smoke. It's actually a brown compound. and gives off a lot of heat. So it's another example of an exothermic reaction. And that heat keeps it going, and it actually looks like it burns a steel wool. But it's another example of something that isn't really burning. There's no oxygen involved. It's just chlorine and iron reacting to form a new compound. So let's do our last element experiment. So last time we experimented with chlorine, which is a halogen gas. And that was a pretty interesting substance, right? And in fact, halogens are very interesting elements because they're very reactive. And I'm going to look at another halogen called iodine. And I thought we might do something a little different this time. Up until this point, we've been taking elements and combining them together into compounds, right? What if we start with a compound and see if we can break it apart into elements? Because reactions can go both directions. They can combine or they can decompose. Okay, so what I'm going to do is, what I have here is a substance I synthesized last night called nitrogen triiodide. And so what that is it's a nitrogen atom combined with 3 iodine atoms. Okay, so let's look at iodine. I have some iodine in that watch glass there. You can take a look at it. So all halogens are toxic, but it turns out that iodine is only very mildly toxic. So it's not nearly as poisonous as chlorine. And in fact, that has some useful properties. They used to put iodine on cuts and scrapes as a way to kill the bacteria. So it's actually got some useful properties. So this iodine looks like kind of a grayish powder, but it actually, what's kind of cool about iodine is it changes color based on what state it is. So for instance, if I put iodine into some alcohol, you'll see it looks brown. See? Pour it into some water, you can maybe see it a bit better. See that? And what's even neater is if you vaporize iodine, if you heat it up to form a vapor, it creates a brilliant blue-violet kind of purple gas. So it's actually a very pretty element. So iodine is one half of our reaction. The other element that's going to be involved is nitrogen. And nitrogen is all over. The thing about nitrogen is it's colorless, it's odorless, it's everywhere, and it really doesn't react with anything. Even when we breathe it in our bodies don't use nitrogen. And that's because nitrogen's a really stable atom. It doesn't really want to react with much. So it's actually quite an accomplishment to get the nitrogen to bond with the iodine, but because of that, nitrogen triiodide is actually a fairly unstable substance. Do you know what unstable means? What?
It doesn't have the correct amount of electrons to make it stable.
It isn't a stable chemical bond, and so the nitrogen triiodide will tend to want to break apart into its individual elements. And in fact, nitrogen is a component in a lot of explosives, because if you can get nitrogen to combine with other things, it'll tend to want to break apart in an explosive reaction. So, are you guys familiar with nitroglycerin? No? Okay. Well, nitroglycerin is, it's an oily, high explosive substance that's actually quite sensitive to shock. Now, I don't personally have any experience making or playing around with nitroglycerin, but I read on the internet that if you put a drop of nitroglycerin on cement and if you hit it with a hammer, you actually have to hit it pretty hard, but if you hit it hard enough, it'll explode just from the force of the hammer. Okay? So nitrogen triiodide, that's the stuff here, and you can see it kind of looks like, it almost looks like dirt, right? It's kind of this black substance that I put on a piece of paper towel. And it turns out that nitrogen triiodide is way more sensitive even than nitroglycerin. I would say it's about 100 times more sensitive. In fact, they say that if you have a fly landing on nitrogen triiodide, just the force of the fly walking on the nitrogen triiodide is enough to make it explode. Luckily, because of our cold Seattle weather, I've eliminated any flies from our garage, so we're safe. So what I want to do is I want to see if I can get this nitrogen triiodide to turn back into its original elements. So those are what? What are the two elements?
Nitrogen.
Nitrogen and iodine. So if we create nitrogen, nitrogen's an odorless, colorless gas, and so it'll just go into the atmosphere. We won't really be able to see that, so that won't be a very interesting part of this reaction. If we create some iodine, if we can get some iodine vapor, we should get some brown or some purple vapor coming off of this reaction. So should we give it a try? Okay, so at this point in the process, I would recommend fingers and ears, hearing protection.
Oh.
Okay, I'm going to do that too. And let's put some gloves on. And I'm going to tap this. I have a very small amount of nitrogen triiodide here. It's maybe 5 grams, perhaps the size of two pencil erasers. And so I'm going to tap it with this wooden dowel and we'll see what happens. See that purple cloud? That's a cloud of iodine vapor. Were you expecting that? And look what happened to our paper towel, and look what happened to our piece of cardboard that we had the nitrogen triiodide on. So, as kind of a finale, that was about 5 grams of nitrogen triiodide. I've actually synthesized about 250 grams of it, and it's in a beaker right by Marie over here. Right over there. And here it is. No, I'm just messing with you guys. This is just a beaker of dirt. It's perfectly safe. Okay, so at this point I feel compelled to talk a little bit about safety. So, you know, everyone likes explosions, right? Especially boys, right, Zach? Yeah. So I think the safest way to experience an explosion is to watch someone else do it on a video, right? You shouldn't try this yourself. And I know I've been casual about what I've been showing you, but in fact, I've done this many times before, and there's actually a lot of safety precautions that are happening that I haven't told you about. So this is not something to try yourself. If you're interested in learning more about explosions and about fire, talk to your science teacher, talk to your parents, and we will be able to come up with a safe way for you to maybe do a few experiments, right? But adults need to be involved. I'm looking at you, Zach. Okay. Okay, well that concludes our second element video. Wow, I think it worked. A little warm in here. Huh? We'll see what happens.